Welcome to my presentation on the results of our research on summarization of loops, in particular of branching loops. This is a joint work with Martin Blicha and William Tatarko, who is actually the main contributor of this work. The loops in programs represent a major challenge in software verification. They're a cause of undecidability in the process of software verification, in particular in software model checking. Their semantics is very hard to capture, and the methods used for capturing the semantics are limited. That is why new methods to handle complex loops or a broader set of loops that really appear in programs are needed. The methods capturing loop semantics can be divided into three groups. The first group is based on loop unbinding. That means we replace the loop by several copies of the loop body, placed one after another. This way, obviously, only a limited number of loop iterations can be captured. In many cases, however, this is a very useful, straightforward, and easy to use method. The second group is based on computing so-called loop invariants. A loop invariant is a formula that is satisfied after any number of loop iterations. It is a very powerful method if it's used the right way, but it is very hard to find suitable invariants, which needs to be both safe and inductive to be of any use during the verification. The third group of methods is based on loop summarization. This is based on capturing the relation between the initial and terminal values of variables that are modified by the loop body. The techniques that are available differ in ability to process complex loop. This is the definition of loop summarization. It is basically a relation that relates the values of variables before executing the loop and after finishing the loop. That is, after basically any possible number of iterations. It is also not easy to compute this relation, that is, to capture, usually symbolically, the values of variables after any possible number of iterations of the loop. Nevertheless, to provide an example, consider the following code. We have this one-liner while cycle which actually increments the value of the x variable as long as x is less than 0. The summary then can be expressed by these two sub-expressions. First, for the negative numbers, so if x is in the set z minus, then the resulting value after finishing this while loop would be 0. Whereas for 0 and positive numbers, the value of the x variable is unchanged. Now we can step to our summarization algorithm, which has, of course, some limitations because the problem of summarization, of capturing the loop semantics, is undecidable in general. So our approach can only handle integer programs with branching inside loops, and we also assume an existence of an oracle for solving relations obtained by the summarization. For this, we used the Z3 SMT solver. The algorithm is based on recursive building of so-called loop diagrams, which I will describe in a while. So, first, a few definitions. A loop branch is a sequence of statements without further branching. If we look at this example, we have a while cycle with an if statement inside it. This if statement has one then branch and one else branch. That means there is a branch A and branch B, or branch 1 and branch 2, or whatever you want to call it. Basically, two branches. A loop diagram basically expresses the possibility or feasibility of executing a sequence of branches. A level diagram has its level. For level 1, I will show an example in a while. It's basically a diagram whose vertices are formed by the particular branches, and there is an edge between the vertices if one branch can follow another branch in the following iteration or in the same iteration. So again, if we consider our example, the loop diagram that corresponds to this source code is depicted at this slide. So we have these two branches, A and B, and the loop diagram looks like this. As you can see, the B branch can be executed at most once, and then there can be several executions of the A branch. The A branch also is the only one of these two after whose execution the whole while cycle can terminate. The algorithm core is based on this function that is called summarize loop diagram, which takes as an argument the diagram D, and according to the shape of the diagram, it performs various operations on it. I will go briefly through the particular steps of this function. This function is recursive, as you can see close to the end of this function, where the function is called itself. So as to the procedure, we first simplify the state diagram, that is, we remove parts that are not really related to the summarization, especially or vertices representing branches, after which execution the whole loop cannot terminate. That means we can get stuck in a kind of live log. If the structure after the simplification is already simple enough, we can sort of directly summarize it. That is split into two cases. First, it can be a trivial loop diagram consisting of just one vertex without any transition, or it can be a simple cycle. Based on these two cases, we either summarize the trivial diagram or summarize the simple cycle. As step 3, we check whether the diagram itself has independent components, that is, if it can be split, and if so, we split the diagram and summarize it part by part. If the diagram is still not simple enough, we need to build a high-level loop diagram and summarize it afterwards. The result is then the disjunction of the summarization of the current level and the summarization of higher level diagram. To the particular steps. So the simplifying of the loop diagram is depicted on this picture. So basically we have a loop diagram and vertex A there, after reaching which the loop simply cannot terminate. So we can remove the vertex A and continue with summarizing the rest of the diagram. The two kinds of loop diagrams that can be directly summarized are, as I already said, a single vertex or a single cycle. A single vertex is a single vertex without any transition, while a simple cycle is a simple cycle without any self-loops or any branching and so on. The summarization of the single vertex is done just by computing the effects of the corresponding statement inside the branch, in this case, inside the branch A. In the case of simple cycle, which is basically the most complicated part of the algorithm, we have to again proceed in several steps. I will going to describe it now. The summarization of simple cycle proceeds in basically 4 steps. First, we compute some partial summarizations that capture the execution from any state of the cycle to some accepting state. But then we assume that no execution of the full cycle after this accepting state appears. So there is basically a finite sequence of branches executed in a row. The third case is that we assume that there is just one execution of this full cycle after the prefix. And the fourth, last and general case is assuming execution of 2 or more iterations of the full loop. And then we combine these partial summarizations. Again, to illustrate it on an example, so assume our simple cycle with 2 accepting vertices A and B, and the partial summarization, again, corresponding to the first step, correspond to those 5 sequences. So as you can see, all these sequences terminates at the A or B vertices, which are the accepting ones. Then the full loop, there are actually 2 full loops, depending again whether they terminate at the A or at the B vertex. BCDA and CDAB, and then we compute summarizations for more iterations. We need to split these two cases, these two last cases, because computing summarizations for more than one, that is two or more iterations, requires the knowledge about iterations or summarization of iterations for just one cycle. So, and this slide shortly describes the computation of summarization for several loop iterations. So we first compute the iteration conditions for IOTAF and IOTAF -1 iterations. That's why we need the requirement that IOTA is at least 2. And this way we capture the effect of IOTAF execution. Then we have to check the so-called monotonicity condition. That is, if IOTA iterations actually were possible, that requires that IOTA -1 iterations are possible or were executed. This is something that doesn't hold always. For example, if the variables changed in a wrong way or the relations are too complex. Nevertheless, if the monotonicity is satisfied as the third step, IOTA iterations are symbolically summarized as a conjunction of these 4 subparts. So the effect of executing IOTA iterations, which is a symbolic value, the IOTA iteration can be executed, so the monotonicity condition holds. Then the fact that basically captures that after IOTA iteration, the cycle is terminated, that is negated of the loop condition after IOTA iteration, and the fact that at least 2 iterations actually were executed. So that's basically it for the simple cycle. Now a few comments on the rest of the algorithm. So splitting into independent parts, as you can see here in these diagrams, we have 2 parts that can be actually analyzed separately. We have to denote the A vertex as an accepting vertex, because otherwise it would be eliminated completely. It would be wrong. And building high-level loop diagrams is, again, one interesting part of the algorithm, which I will describe in more detail. So this procedure is applied when the current loop diagram is too complex, and building a high-level diagram can help to simplify the diagram at the end, actually. So assume a very simple diagram like this. So we have 2 vertices here, B and C, with a self-proof in C, so it's not a simple cycle. So we need to build a high-level diagram. This high-level diagram is not built just from the level 1 diagram. That means that we need to take into account also the feasibility of the particular sequences of branches. So the level 2 diagram is computed. It is still not a simple cycle or something that can be directly summarized, so we have to continue. We have a level 3 diagram here, which again is the case that it's too complex to summarize directly. So we built a level 4 diagram, and this diagram already can be split and summarized by part by taking into account just the C vertex and the simple cycle that remains afterwards. And this is the basic idea. We have also implemented the work in a prototype Python tool that is called W Summarizer. It employs, as I already mentioned, the Z3 SMP solver to decide about feasibility of branch sequences. And we performed a simple experimental evaluation, which actually looks very promising, and I will present the results now. So the evaluation is based on comparing the performance with state-of-the-art tools, in particular its load, Flutter, and Z3 itself. And the input that we used for the comparison were created based on the SAC'22 benchmarks. For the case of Z3, which is not able to complete the summarization directly, however, it is able to check the feasibility of particular number of loop iterations. So that is what we actually have used for comparing the performance. At this slide, you can see the comparison of the results for particular tools. As you can see, our W summarizer was able to compute the summarization for almost all considered inputs. There is just one exception. So in this case, it can beat both load and flutter. Z3, which was able to validate the summarization or branch sequences for all the cases, for all the inputs, we also focus on the performance in terms of time to compute the summarization or validate the branch sequences. And this is the content of this slide. So basically, as I already said, Z3 was used just to decide the formula, formally encoding the loops. And as you can see, the Z3 performance, the required time to compute or validate the sequences, depends exponentially on the number of iterations. However, our W summarizer is not sensitive to number of iterations, and it can compute the summarization for any number of loop iterations. So that's it. As a future work, we plan to properly implement this algorithm, probably in C and C++, and use it for an extensive evaluation of this approach. We believe that actually using that in a portfolio can significantly contribute to the overall performance of the verification process. And we are at the end. In this talk, I have introduced a new competitive algorithm to you for branching loop summarization. It is implemented in a prototype Python tool that is called W Summarizer, and that employs Z3 assembly solver. As I already said, we see a significant potential to contribution of the verification performance when it is used in a portfolio. Thank you very much for your attention.